presenter will be Phil, and his presentation is about scalable, reliable instant messenger using the SD Erlang library.
Thank you. In a change to the schedule, I'm going to start with a brief advert. So there's a new MOOC in Haskell, and in case you have students who might want to learn it, perhaps for a project, or you want people know people who are interested in a fun job. So it's hosted out of Glasgow. It's running in cohorts. So the first cohort started about a week ago. There was already about 5,000 people signed up, and it seems several thousand were actually doing something on the course, which is interesting. It's about 6 weeks long. Uses essentially based on the Haskell interactive programming environment. It covers core Haskell, but not every possible corner, and it's really about how to think functionally. And it's fairly easy to find if you Google for the Haskell MOOC, or follow the Twitter account, or visit the URL. Okay, so what I really came here to talk about is a benchmark looking at how to build scalable, reliable systems in Erlang, and in particular an instant messenger. And this is joint work. In fact, the guy who did most of the work is Mario Hernandez, and Natalia did more of it, and I'm just here for boring reasons. So I'm going to give you some background, talk about the design and implementation of our instant messenger, talk about reliability, and show you some results from experimenting with the system. So reliability in Erlang, the key thing is that the process is entirely isolated, so a failing process doesn't poison the rest of the system. And I'm very glad that Maria talked already about message passing. There's strong dynamic typing, and the key mechanism is the supervision trees, one process supervising another. Okay. What are the limitations when you build distributed systems? Well, when two Erlang nodes connect, they share their sets of connections, all the other nodes they know about, and quickly your distributed Erlang system becomes fully meshed. Every node is connected with every other node. So in a system with n nodes, you quickly land up with n squared connection links. These are actually active TCP/IP links, so there's communication to keep the link alive. And this limits the scalability of the system. So the graph on the left here shows the scalability. So on the x-axis is the number of nodes, and the number in brackets is the number of cores. So this is 50 nodes, 100 nodes, 150 nodes, 200 nodes, up to 256 nodes. With from 1200 to just over 6,000 cores. And the program we're measuring, and really you only need to concentrate on the red line, is a program that simply does a massive computation. I'll say a little bit more about it, but over this connected mesh of nodes. And what happens is, for large computations, it ceases to scale around about 40 hosts. Simply maintaining all of these connections. So having the connection, or creating the mesh of connections is great for transparent distribution, what Maria was talking about. You don't have to care about where the actor is. You just send it a message, and the message is automatically routed for you. And that works fine up until you've got about 40 or 60 hosts. But thereafter, the underlying communication costs eat your lunch, and the system doesn't scale. And I'll explain why this system scales better shortly. Okay, the other problem with distributed Erlang is that one of the reliability mechanisms is that you register the name of a process, so that if the process dies, you can restart a new instance of the process, give it the same name, and clients of that process can find it. That's exactly the same mechanism Maria talked about, having a persistent actor ID or something. Right. But these are global, it's global information that is shared amongst all of the nodes of the system, and it's actually done synchronously. And if you register, if you have to keep the global information, so every node has to get a copy of this information, that really limits your scalability. So this is a system that does a large number of operations, random operations. Some of the operations are done locally, others are just between a pair of nodes from one to another, like sending a message. And the third class of operation is global, where you do an operation that has to be performed, like registering a name, on every node in the system. And even if you just have 0.01%, 1 in 10,000 operations are global, this is sufficient to limit your scalability. So the red curve is doing this in distributed Erlang. So when you get to about 40 hosts, you just can't register these. The global operation is limiting your throughput, the number of messages you can send per unit time. Okay, so in a recently completed European project, we studied the scalability of distributed Erlang, and those were some of the key results. And then we designed something called Scalable Distributed Erlang, or the SD Erlang libraries. And the idea is we partition the sets of nodes into groups. It's called S groups. We also provide semi-explicit process placement that I'm not going to talk about at all. And we aim to preserve the reliability mechanisms of Erlang. So, it hasn't been updated. We plan to update the library to Erlang, to OTP 19.0 next month. It's currently on 17.4. Okay. Thus far, we have looked at the performance of SD Erlang, and we run it on a couple of benchmarks. One's called ACO, which is a parallel simulation benchmark, and the other one is called Orbit, which is it's actually an algebraic computation, but the key underlying data structure is a distributed hash table. So you hash to determine where you're going to put the data, which looks a lot like some of the stuff that Maria was talking about. But the underlying data structure is pretty similar to what you see in a NoSQL DBMS like React, except in React it's replicated. But both of these benchmarks are pretty small, and they have fairly simple reliability mechanisms. And actually, the results I showed you here, if you do these global operations only within a fixed size S group, so you do the operations but make them global only within the S group, you can recover the scalability. So that's what the blue curve is about. And this curve here is looking at the scalability of Orbit using SD Erlang, where you've broken the distributed hash table into clusters or groups of nodes. Okay. So, in contrast to the evaluation we've done previously, this instant messenger is much more typical of an Erlang application. It's a reliable server. It's quite a bit bigger. It's about 6,000 lines of code, whereas these are a few hundred. It does reliability fairly seriously. We recall, we keep databases of current chats that are happening so that we can recover the chats that are in progress after a failure. It uses throughput as the performance metric, whereas Orbit is using strong scaling and ACO is using weak scaling. And because of this reliability mechanism, we actually do some fairly careful reliability evaluation. Okay, so instant messengers. You might have heard of WhatsApp if you're in the Erlang community. You might even use a few of these things. Our IM benchmark has a client and a server side. There are two versions. There's one built-in distributed Erlang, that's a reliable distributed instant messenger. We also built an unreliable one as a first stage. And then we have a reliable SD Erlang, which is simply RDIM refactored to introduce S groups. The client side, we essentially simulate chat server user behavior using kind of published metrics for how long chats are and how frequently people send messages. Okay, and this looks again a whole lot like what Maria said. You have clients who send messages. These are routed to servers, and then once they've been routed, the server then manages the chat between the clients. This shows the live connections in the IAM. Sorry. The connections that are maintained. If, however, you break it into S groups, then the structure looks like this. You have an S group for each router, so the router is in touch with only its own servers, and the routers are part of a kind of master S group. And you can do produce an analytical model of how much fewer connections there are, but probably just looking at the picture, you believe me that there are fewer links on the right than on the left, but in fact, it's always true. The software architecture is reasonably complex. We have a router node with a pair of supervisors, a router supervisor and a router supervisor monitor. So these supervise each other in case of failure. A router processes spawn servers, and it's a server monitor that monitors the client and the chat session, maintains a database of clients and a database of current chat sessions, and I said that already, and the client monitors spawn, the client processes too, and these databases are replicated X tables. There's two kinds of clients. You can have a normal client and you can actually send messages, but we want to measure these things at scale, so we actually have to artificially generate a bunch of traffic, because we don't have thousands of people who want to chat to each other. We're computer scientists after all. Reliability, I don't think I'm going to talk about this. It's in the paper. It describes how you can recover if there are failures. So let me show you some performance results for this. So it's run on a Beowulf cluster. So there's 17 hosts, there's 16 core hosts, so a total of 272 cores, I think. It's running under Scientific Linux, and it's Erlang OTP 17.4 or SD Erlang 17.4. What happens when you introduce the S groups? Firstly, how much of a performance hit do you have? So this is S groups. What we do is we vary the number of servers, 4, 5, 7, 9. Oh, okay, so I think the reason we have 5 is there's one master node and then 4 servers, one master and 6 servers, etc. 8, 12, 17. And you'll see that the dotted lines are pretty close to the solid lines. The overheads are pretty small. We're handling, once we get up to 17 nodes, 16 servers, we're handling around about 1.5 million messages a minute, and it takes about 2 minutes for the system to reach a stable state. If we take the maximum throughput with 4, 5, 7, 9 nodes and we plot that, so we take the number of nodes and plot it against the throughput, you'll see that we're scaling pretty linearly, both RDIM and RSDIM, and we haven't hit any scalability limits with 17 nodes. Oh, by the way, all of these measurements at present are without failures. I'll come to reliability and failures in a minute. What happens, so that's with only one router, what happens if we introduce a second router? Well, we see very similar patterns. Both implementations perform similarly, but if you compare the curve fit from the previous graph with one router with the performance you get for RDSIM with 2 and RSDIM with 2, the performance has degraded slightly. So introducing a second router has made the performance slightly worse. Very simple point. What about introducing more routers, so 2, 3, 4? Well, basically they just make things worse. In fact, now, for the first time now, the SD Erlang, we compare the purple with purple and blue with blue. For the first time, the SD Erlang is significantly worse, well, significantly 10% worse than the original distributed Erlang. And the issue is each router has an S group, sets of S groups, so we're introducing a lot more small S groups, and we're paying a penalty for doing that. But you don't have to do that. But even if you do, it's only about 6 or 7%. Okay, failures, right. So, in order to measure failures, we introduced a version of Chaos Monkey, which randomly kills processes in the system. You set a start point, at which point you're going to start introducing failures, and then a failure rate. Now, in our application, we have many more, as in thousands more client monitoring and chat sessions than we have any other kind of process. So if we choose processes at random, then we're not going to kill very many of the interesting and unusual processes. So we have created a version called Rhesus, and you can choose a probability for the different classes of process, which means you can kill more of the rare processes than a naive Chaos Monkey does. So it's a very slight wrinkle on the Chaos Monkey. Oops. And so this shows the throughput with 12 server nodes. When we use Rhesus to terminate different types, all the different types of IM processes with different failure rates. So the red curve is when there are no failures, and then the different coloured curves are different failure rates. Failure rates at 15 seconds, 10 seconds, 5 seconds. There are 1 second, and then we kill the database processes, the X tables only, and nothing really causes major problems. There's small performance impact, about 3%. Oh, notice the scale here. The red line is running somewhere between 1.15 million transactions, and this bottom line here is 1.105. So the scale here is really quite narrow. What do we conclude? The IM is exactly the kind of thing we needed to try SD-Erlang out on to convince people that it's a useful library, we hope. We've measured it at small scale, so the first graphs I showed you, we were running on really big, essentially HPC clusters with hundreds of nodes. We don't have access to those at the moment, so we've only measured this up to about 17 nodes. Introducing the S groups doesn't have any measurable performance penalties. If you make the S groups introduce redundant router nodes or lots of small S groups, there are small performance penalties, but that's just poor design. You can easily avoid that kind of design choice. Both RDIM and RSDIM tolerate failures with minimum impact on throughput. And I'll say some more about just how quickly Erlang recovers from failure in comparison with some conventional technologies this afternoon. But the take-home message is SD-Erlang preserves the distributed Erlang reliability mechanisms of particularly supervision trees and persisting key state. What's next? We'd really like to measure this system on a large cluster or a big cloud instance, and we haven't. It'd be nice to have, in order to do that, we'd have to have a traffic generator that's capable of generating the traffic to exercise the big system. So we'd have to re-engineer that traffic generator. And currently, the routing of messages between S groups is explicit. In order to send a message, if you don't have a connection to a node, you need to send a message to a gateway node that does have a connection, at least transitively, to that node. And you have to write the code to forward these messages. And it would be nice to automate that. And that's a project. That's it.
So I'm a bit puzzled. You started off showing us that up to about 40 nodes, distributed Erlang didn't have scalability problems.
Yeah.
But beyond that, SD-Erlang can give good improvements. Around 100 nodes, you're getting a big improvement. But now these experiments you've done with 17 nodes.
Yeah.
Is there any reason to run SD-Erlang on a cluster of that size?
No. But, well, there are scientific reasons that there aren't, you wouldn't, I guess, hope to see performance benefits, but you can look at what performance penalties might be, and you can look whether SD-Erlang can preserve the reliability mechanisms.
So you're trying to show that SD-Erlang did not screw things up?
Yeah, and critically, I mean, this is really about showing the reliability mechanisms work, and I guess I'm asking you to believe that the reliability mechanisms that work when you have 17 nodes and 270 cores will also work when you have 100 nodes and 1,000 cores.
So I didn't quite understand the results for the reliability
Aha.
mechanisms. Because, so my question was, you seem to be talking about the performance penalty
Yep.
of killing processes. But what about functionality? Were all messages delivered nonetheless, or not?
Aha. Good point. Good point. So how much chat information did we lose? And I don't know the answer to that. I don't know the answer to that. I can find out and let you know. But yes, so one of the key things is how much information did we lose? The purpose of the chat databases is to recover the chat sessions, but whether any of the messages that were in flight were lost, and I think there could be. So I think some of those messages could have been lost.
Then it would be interesting to know whether Erlang loses more or fewer messages than
Indeed.
distributed networks.
Indeed. Indeed. Yeah. Good point.
Kendra, please.
Just curious, what if the number of nodes will be increasing to 1,000, to 10,000? Any kind of perspective you have that the SDR will scale, or not, or any kind of failure expectation?
I believe it will scale. So the point is that the messages are local within the groups, and if the groups have a fixed size, so one of the design decisions when you refactor a program into, so this is up to 100 nodes, when you refactor a program from Erlang into SD-Erlang, one of the decisions you have is how big are the S groups. But if you keep the number of S groups, the size of the S groups as a fixed size, so I don't know, 10 nodes in each S group, you might then think, oh, but if you build your architectures like this, then maybe you'll get this S group will become very big, because if you only have 10 nodes in each of the per router, then on 1,000 nodes, you might then have 100 routers. But in fact, our ACO benchmark we built with an hierarchy of master nodes. So there you have a root group. Essentially, it's a tree of S groups, and you can, certainly for the ACO benchmark, which we did measure on hundreds of nodes, 256 nodes, you use a hierarchy of S groups. So I think for many applications it will be possible to keep the size of the S groups to a small constant, and I think if you can do that, then they should scale. The communication path then becomes longer between the leaves of that tree, because you have to go through more gateways.
One of the things I asked about 10,000 or 10,000 is that in the real world applications such as React, already 100 or 200 nodes of React processes are already in the production. So if you, I'd like to suggest that testing React with 1,000 or 10,000 nodes on the SDR might be a very good benchmark.
So we in the release project we studied the scalability of React and published a paper in the Erlang workshop 2013 or 2014 looking at the scalability of React. It is possible to build Erlang systems that scale to hundreds of nodes, but you have to depart from the distributed Erlang model. You have to start using hidden nodes and avoiding this fully connected mesh and doing your own routing. So I suppose one way of thinking about SD Erlang is it is a disciplined way. We're trying to build a systematic way of partitioning this fully meshed mechanism.
We should continue. So
Please grab me at the coffee break. I'm very happy to talk.
Coffee